Welcome back to K11 Tech University. So far, we've wrestled with combinatorial explosion, we've learned how to intelligently prune massive search spaces, and we've reframed backtracking as a structured search. But what if I told you that all of these ideas, they're all powered by the exact same engine? That's right. Every single one of these powerful techniques, from navigating huge decision trees to cutting them down to size, they all stand on the shoulders of one single foundational concept. And today, we're going to finally put that concept under the microscope. Today is all about explaining recursion properly. And we're going to do that by learning to think in terms of self-similar problems. And look, we're not just going to throw a textbook definition at you. The goal here is to build a completely new mental model for how you solve complex challenges. Okay, but before we can build up this new way of thinking, we have to tear down some old ideas. It's actually just as important to understand what recursion is not. So let's start by clearing away some of the fog, some of the common myths that get people tangled up. All right, let's get this out of the way right now. Recursion is not a specific algorithm, like sorting or searching. It is definitely not a performance optimization. In fact, a lot of the time, it's the opposite. And it is absolutely not just some fancy, complicated way to write a loop. Thinking any of these things is a trap. So if it's none of those things, then what is it? At its heart, recursion is a problem-solving philosophy. It's a way of looking at a big, messy problem and saying, hey, what if I could solve this by just solving a smaller identical version of it first? And that right there, that idea of an identical version, brings us to the absolute core concept that makes the whole thing work: self-similarity. If you get this, you get recursion. So how do you know if a problem is a good fit for recursion? Well, it has to pass 3 simple tests. 1, you have to be able to break it down into smaller pieces. 2, and this is the critical part, each of those small pieces has to look just like the original problem, same structure. And 3, there has to be a stopping point. We call it a base case. It's the point where the problem is so tiny, so simple, that you can just solve it outright without breaking it down any further. And I really want to stress this. That base case is non-negotiable. It's not a suggestion. Without a clear finish line, your process doesn't solve anything. It just runs forever until your system runs out of memory and crashes. Now, once you start looking for it, you see this pattern of self-similarity everywhere. A folder on your computer can hold files, but it can also hold other folders. It's the same structure nested inside itself. Or think about a tree data structure. What's it made of? A root node and a bunch of smaller subtrees. This pattern, a thing containing a smaller version of itself, is the telltale sign of a recursive problem. Okay, so this all makes sense conceptually, but how does a computer actually keep track of all this breaking down and solving? The best way to picture it, conceptually, is as a stack of deferred work. Picture it like this. A function gets a job to do. It starts working, but then it hits a recursive part. What does it do? It literally pauses everything it's doing. It then delegates a smaller version of the problem to a brand new call of itself. It then just waits. And only when that smaller job is completely finished and returns an answer does the original function wake up and resume its own work. And this is where the cost comes in. Every single one of those paused jobs has to be remembered. The computer has to write down a little note for each one saying, here's where you left off. It stores all these notes on something called the call stack, and that stack of pending work is exactly why recursion uses up memory. It's a trade-off. This is the simple, powerful contract at the heart of recursion. Each task is essentially telling the next one in line, I'll finish my job, I promise, but only after you finish yours. It's a chain of trust. You see, once you pull back the curtain, it isn't some kind of mysterious magic. Recursion is just a really organized system for putting work on hold. That's the mental model you want. It's just deferred work. All right, now that we have this mental model, we can finally tackle the big practical question. When should we actually use this? This brings us to the classic engineering showdown: recursion versus iteration. Recursion really shines when the problem you're solving looks like a Russian nesting doll. Things that are naturally hierarchical, like a file system or a family tree. In these cases, a recursive solution can directly mirror the shape of the data, which makes the code incredibly clean and easy to understand. But, and this is a big but, recursion can be dangerous. If you can't control how deep the calls go, or if you're working with limited memory, you risk a stack overflow, where you literally run out of space for all those paused jobs and your program crashes. Hard. A good engineer knows when a simple loop is the smarter, safer choice. So here's the fundamental trade-off side by side. Iteration, using loops, gives you explicit control, predictable memory, and it's often faster. Recursion, on the other hand, often gives you a cleaner, more elegant solution that perfectly matches the problem, making it easier to prove that it's correct. So please, burn this into your brain. One is not better than the other. This isn't about style points or which one you prefer. It is a deliberate engineering choice that should be driven entirely by the shape of the problem you are solving. And look, getting this right isn't just about passing a coding interview. It's a genuine turning point. It's a level up in how you approach problem solving in general. Let me show you what I mean. Without a solid grasp of recursion, things like backtracking feel like magic. Dynamic programming seems totally arbitrary. But once you get it, search strategies just make sense. Dynamic programming becomes the obvious, inevitable next step. The complexity becomes visible, and you stop just memorizing algorithms and start reasoning about them. That's why we're spending so much time on this one idea. This understanding isn't the final destination. It's the bridge that gets you from where you are now to all of the really powerful advanced topics in computer science. And speaking of where we're headed next, we're going to take this abstract idea and make it completely visual. We're going to draw out recursion trees, analyze them, and see how to spot wasted work and overlapping subproblems. And that, right there, is the doorway into the world of dynamic programming. So we'll leave you with this thought. Recursion isn't really about the code you write. It's about seeing the hidden structure in a problem and having the trust that the smaller versions will do their job so you can focus on yours. This is K11 Tech University. We'll see you in the next lecture.